So, today let us go over a couple of problems. The first problem deals with evaluation of Gibbs free energy, enthalpies and entropies of a substance based upon the knowledge of heat capacities at constant pressure, and the second problem deals with calculation of entropy changes associated with the irreversible process of heat transfer. So, we have seen Gibbs free energy is a state function and it can be expressed as G is equal to H minus T s, and we can use Gibbs free energy as a criteria for equilibrium with temperature and pressure as the independent variables. But how to evaluate these Gibbs free energies? So, basically we need to evaluate the enthalpies and entropies, and from which we can evaluate the Gibbs free energies. So, how do we get to enthalpies and entropies of a substance? So, here the heat capacity becomes quite useful. We know that the heat capacity at constant pressure is defined as heat absorbed at constant pressure per unit rise in temperature. So, Cp is equal to delta Qp by dt. So, note small heat effects by delta, because heat is a path function, and we are denoting small differences in temperature by dt because T is a state function and we can define the exact differential. Now, we know heat absorbed at constant pressure is basically the change in enthalpy. So, we can write this as delta Qp is equal to dH. So, Cp is equal to dH by dt. So, basically dH is equal to Cp dt. Similarly, in order to get to entropy, we can use the first law of thermodynamics. So, delta Qp can be replaced by du plus delta W, change in internal energy, plus the work done, and du can be replaced by the combination of first and second law. We know du is equal to Tds minus Pdv, and delta W is Pdv by dt. So, basically we get ds is equal to Cp by T dt. So, let us get to first the enthalpy. So, based upon this, if we make a state change and the temperatures of the two states are T1 and the second state is T2, then we can write delta H for the state change as H at T2 minus H at T1 is equal to integral Cp dt from T1 to T2. So, basically to get to the enthalpy at any temperature T2, we need to know enthalpy of at one temperature T1 and the knowledge of Cp as a function of temperature. So, typically Cp are measurable quantities because we can measure the heat effects, and so there are databases available for Cp as a function of temperature over the different ranges of temperature for different materials. So, from there we can evaluate these integrals Cp dt, but what about the enthalpy at temperature T1? So, as I said last class, these properties we cannot evaluate the absolute quantities like enthalpies and Gibbs free energies, but it is sufficient to know the differences in these properties while going from one state to the other. So, in other words, we can use enthalpy at one temperature as a reference point and can evaluate the enthalpies with respect to that reference. So, typically the convention for enthalpy is the enthalpy of a pure element in its stable state at 298 Kelvin is taken as 0, right. So, enthalpy of a pure element, this is important, in its stable state at 298 Kelvin is taken as 0. This is important. At 298 Kelvin, the element in its stable state has 0 enthalpy by this convention. So, that is taken as the reference state for enthalpy evaluation. So, for example, iron we know at room temperature at 298 Kelvin exists as BCC. So, enthalpy of BCC ion at 298 Kelvin is taken as 0, but enthalpy of FCC ion at 298 Kelvin will obviously have some non-zero value. Then for entropy we can write delta S is equal to S at T2 minus S at T1 equal to integral Cp by T dt. So, S at T2 is given as S at T1 plus integral T1 to T2 Cp by T dt. So, what about the reference for entropy? So, here we use the third law of thermodynamics. What is the third law? So, the entropy of a homogeneous substance in complete internal equilibrium is 0 at 0 Kelvin. Okay. So, that is the third law of thermodynamics. So, this is important, the substance has to be in complete internal equilibrium, right. For example, as any crystalline solid for example, has some equilibrium vacancy concentration at any temperature above 0 Kelvin, right, and it is a function of temperature. So, vacancy concentration increases as the temperature increases. So, as you decrease the temperature, vacancy concentration should decrease with the temperature, and so at 0 Kelvin the vacancy concentration should reach 0, but this does not usually happen. The excess vacancies have to be annihilated at the sinks, and so as you cool down the kinetics becomes very slow, and so the vacancy concentration cannot approach equilibrium vacancy concentration at lower temperature. So, at 0 Kelvin if you could reach 0 Kelvin, we would still have some vacancy excess left over, and so for that solid then the entropy at 0 Kelvin will not be 0. Okay. So, we assume basically that at 0 Kelvin there will be a pure crystalline solid without any defects. So, entropy can have absolute values evaluated based upon the third law of thermodynamics. So, there are data tabulated for standard entropies at 298 Kelvin. Okay. So, in the tabulated data you will find those. So, based upon knowledge of Cp versus temperature, we can get to the enthalpies and entropy, and then from it we can evaluate the Gibbs free energies. So, the Cp is typically expressed as a function of temperature. The empirical formula in the tabulated data usually is A plus Bt plus C by T square. So, for example, I have listed Cp's for some of the materials. So, you can see for aluminum solid the heat capacity is 20.67 plus 12.38 times 10 to the power minus 3 T. So, the value of A here is 20.67 and B is 12.38. If you look at oxygen gas, the value of A is 29.96, B is 4.18 times 10 to the power minus 3, and C is minus 1.67 times 10 to the power 5. Okay. So, based upon this, let us say if we want to evaluate Gibbs free energy of 1 mole of aluminum at let us say 800 degree centigrade, that should be enthalpy of aluminum liquid at 800 degree centigrade minus T times entropy of aluminum liquid at 800 degree centigrade, right. 800 degree centigrade is basically 1073 Kelvin. So, if we write the formula for enthalpy of aluminum liquid at 1073 Kelvin. So, how do we go about this? We know the enthalpy of aluminum solid at 298 Kelvin, right, which is by convention 0, right. So, we know that H of aluminum solid at 298 Kelvin plus we know how the Cp of aluminum varies with temperature. So, we know integral Cp dt from 298 to the aluminum will melt in between, right, before we reach 1073 Kelvin. So, it melts at 934 Kelvin. So, we can use Cp solid only up to 934 Kelvin. Then when aluminum melts, it will absorb heat, right. So, we need to consider that latent heat of melting. So, delta H melting of aluminum at 934 Kelvin, and then aluminum becomes liquid. So, we have to heat a liquid aluminum from 934 to the temperature desired, that is 1073 Kelvin. So, Cp dt, this is Cp of aluminum liquid. The first integral Cp is for aluminum solid. Yeah. Delta H melting of aluminum at 934 Kelvin is 10,700 joules per mole. So, if we substitute H of aluminum solid at 298 Kelvin is 0 plus Cp of aluminum solid integral 20.67. So, 20.67 times 934 minus 298 plus integral T dt is T square by 2, 12.38 into 10 to power minus 3 by 2, 934 square minus 298 square, and the enthalpy of melting of aluminum is 10,700 plus aluminum liquid, the Cp of aluminum liquid is constant. So, 31.76 times 1073 minus 934. So, this comes out to be 33,110 joules. So, now next we evaluate entropy. So, entropy of aluminum liquid at 1073 Kelvin can be written as entropy of aluminum solid at 298 Kelvin plus integral 298 to the melting point 934 of Cp. The Cp is of aluminum solid, Cp by T dt plus integral 934 to 1073 Cp of aluminum liquid by T dt, and then at 934 there is a melting occurring. So, we need to consider the entropy of melting of aluminum at, this is the equilibrium melting point is 934 Kelvin. Okay. So, this is tabulated data. We know entropy of aluminum at 298 Kelvin is 28.3 joule per Kelvin per mole plus Cp of aluminum solid by T. So, if we look at Cp of aluminum solid, integral of 20.67 by T dt will be 20.67 ln T. So, the limits are 934 ln of 934 by 298 plus 12.38 into 10 to the power minus 3, 934 minus 298 plus integral 31.76 by t dt, that will be 31.76 ln 1073 divided by 934, and then finally we need the entropy of melting. How do we get to this? We know the enthalpy of melting, and at equilibrium melting temperature we know delta G melting will be 0, right, because at equilibrium melting solid is in equilibrium with liquid. So, if we change the state from solid to liquid, there should be no change in Gibbs free energy, which we know is equal to delta H melting minus Tm delta Sm, and so delta Sm is nothing but delta Hm by Tm. So, we know delta Hm is 10,700 divided by 934. So, we get delta Sm, which will be 10,700 divided by 934. So, if we evaluate this, we get the entropy of aluminum at 1073 Kelvin to be 75.64 joule per Kelvin per mole. And so, once we know H and S, we can know Gibbs free energy of aluminum liquid at 1073 Kelvin is equal to 33,110 minus 1073 times 75.64, which comes out to be minus 48,050 joule per mole. Okay. So, this is how we can get to the Gibbs free energies of the substances based upon the tabulated data of heat capacities at constant pressure. So, heat capacity becomes a very useful parameter. Again, it can be experimentally determined, tabulated, and can be used to generate the Gibbs free energy data as a function of temperature. Okay. Any question? Okay. So, let us take a look at another problem. This is basically the problem of evaluating the changes in entropy when the heat transfer takes place, obviously from hotter body to the colder body. This is an irreversible process, right. So, suppose we have a container of oil which is at normal temperature, the room temperature, that is 27 degrees centigrade, basically 300 Kelvin, and we drop a piece of steel, right. The temperature of steel before dropping is 427 degrees centigrade, which is like 700 Kelvin. So, as soon as we drop the steel piece in the oil, there will be heat transfer from steel piece to the oil. So, the temperature of steel will come down, temperature of oil will increase, and the heat transfer will continue until the equilibrium state is reached. And what is the equilibrium state? The equilibrium state is when there is a uniform temperature of oil and steel. Okay. So, what is that temperature T? So, we first need to evaluate the temperature T. So, we need to know the quantity of oil and steel, of course. So, let us say the mass of steel is 30 kg and mass of oil is 150 kg. Of course, we need to know the Cp. So, Cp of steel is given to be 0.46 kilojoule per kg per Kelvin, and Cp of oil is given to be 2.5 kilojoule per kg per Kelvin, and this is occurring at all constant pressure of 1 atmosphere. So, what is the change in entropy is what we need to calculate. So, first we need to get at the final temperature of the system of oil plus steel, right. So, this container is given to be an perfectly insulated container, which means there is no external heat effect. The heat is transferred between steel and oil, but there is no external heat effect. So, this we can know based upon the CP data, we know how much heat transfer is occurring. So, whatever heat lost by steel should be equal to the heat gained by the oil, right. So, we can write mCp. So, this is for steel, delta T is equal to mCp delta T for oil, right. This is for steel, and this we have to consider the magnitudes, right. So, we can write (30 times 0.46 time), let us say T is the final temperature, that will be 700 minus T should be equal to 150 into 2.5 times T minus 300. So, if we solve for T, we get T is equal to 314.2 Kelvin. So, the final temperature of oil plus steel system will be 314.2 Kelvin. So, now let us evaluate the entropy change. So, for steel you can write delta S steel is equal to delta Q integral delta Q by T, and we know pressure is constant, and so delta Q QP heat absorbed at constant pressure. So, that should be equal to integral dH by T or integral Cp dt by T, and we know the integral is from the initial temperature of steel was 700, and the final temperature is 314.2. So, this should be equal to 0.46 ln 314.2 divided by 700, and this has to be multiplied by mass because Cp is given in terms of per kg. So, this multiplied by 30. So, obviously 314 is less than 700. So, this logarithm of it is negative. So, the entropy change for steel is negative, it comes out to be minus 11.05 kilojoule per Kelvin, which is obvious, right, because steel is losing heat. So, heat is rejected by the steel. So, the entropy has to decrease, there is no other external heat effect. Similarly, for oil we can write M oil Cp oil ln the initial temperature, the final temperature of oil is again 314.2 and the initial temperature was 300 Kelvin. For oil obviously heat is being absorbed by oil. So, there is an increase in entropy. So, obviously the entropy change is positive 17.34 kilojoule per Kelvin. So, if you consider oil plus steel as this system, then we have delta S steel plus delta S oil, and which should be positive, right, minus 11.05 plus 17.34. So, the net entropy change for the system is positive because it is adiabatic, right. The walls are given to be insulated, perfectly insulated, constant temperatures at constant pressure.
Extensive property, but when
Temperature is an intensive property. Okay. So, any question so far? All right. So, we will stop here.